Imagine a single point of failure. A circle of rubber no wider than your hand, supporting 20 tons, spinning hundreds of times per minute across thousands of miles of boiling asphalt, freezing cold, and broken roads. Now multiply that point by 18. 18 fragile interfaces between a 600 horsepower vehicle and the abyss. What monitors those 18 critical points 24 hours a day? It's not the driver, their senses are limited. It's not a mechanic, they're hundreds of kilometers away. The answer is there for all to see, spinning with hypnotic persistence. Those small metal tubes protruding from the center of truck and bus wheels. They are not an ornament or an accessory. They are the sentinels. They are the spearhead of a silent and relentless war being waged at the very edge where rubber meets the road. A war against physics, against wear and tear, against bankruptcy, and above all, against catastrophe. Today, we will not only tell you what they are. We will show you why, without that little spinning tube, modern global transportation would come to a halt. Breaking down the CTIS, Central Tire Inflation System. To begin this journey, we must give our mysterious protagonist a name. Those rotating valves are the visible part of a system with a name that sounds like military technology, because to a large extent it is. The Central Tire Inflation System, or CTIS for short. Those four letters encapsulate a radical philosophy. Tire pressure can no longer be a reactive, manual, and human error-prone affair. It must be an automatic, centralized, computer-managed function. The central is key. It means there aren't 18 separate systems, one per wheel. There is a single brain, usually an electro-pneumatic control unit, which governs from a strategic point on the chassis. This brain receives data, makes decisions, and sends commands. Inflation is its most obvious function, but it is only one facet. Its real mission is control. Controlling pressure 24 hours a day. Controlling the response to a failure. Controlling even the way the vehicle interacts with different terrains. The system is what ties it all together. A network of high-pressure air hoses, specialized valves, electronic sensors, and an interface in the cab. Calling it an automatic inflator would be like calling the human nervous system a tickle transmitter. It completely underestimates its sophistication. The CTIS is the truck's autonomous nervous system, dedicated to one vital task: maintaining the integrity of that single point of contact with the world. And it all starts with the most eye-catching component, the part that spins non-stop. How a rotating valve defies physics and seals air at 100 kilometers per hour. The biggest engineering challenge of the entire CTIS system is seemingly simple, but physically daunting: connecting a stationary air hose, fixed to the axle, to an inner tube spinning at over 100 kilometers per hour. Think of trying to inflate a bicycle tire while it's moving, but with pressures 10 times higher and with the requirement that not even the smallest air bubble escape. The solution is a precision-engineered part called a rotary valve or rotary union. That small metal protrusion you see is just the head of a much more complex device. Inside, anchored to the axle, is a stationary body through which air from the main system enters. Attached to it, and rotating with the wheel, is a moving housing that directs the air to the tire. The miracle occurs at the interface between these two parts, a dynamic seal, usually made of advanced composite materials such as PTFE, Teflon, reinforced with graphite or bronze. This seal allows the rotating part to rotate freely thousands and thousands of times, while maintaining a tight seal against pressures that can exceed 10 atmospheres. It is lubricated by the air in the system itself and designed to withstand a particular hell. Brutal vibrations, stone impacts, immersion in mud, jets of salt water, and the heat generated by brake friction. That such a critical component is exposed to the elements is not an oversight. It is a statement of confidence in its robustness. Its failure would be catastrophic, so it is built to be the most durable part of the assembly. This valve is the physical bridge, the point where the central nervous system of the CTIS literally touches the wheel. It is the gateway to and from the life of the tire. Through it enters the air that keeps it alive, and through it, as we shall see, escape the first signs of its possible death. The silent alert. From the wheel to the cab, the journey of a signal that saves lives. Now, let's transport ourselves to a critical scenario. A loaded truck is traveling at night on a deserted highway. A sharp piece of metal on the asphalt punctures the sidewall of a rear tire. Air begins to escape. In a truck without CTIS, the first sign for the driver would be a subtle vibration in the steering wheel, a slight tilt of the trailer, or the sound of rubber disintegrating, which often comes too late. With CTIS, the alarm sounds the moment the pressure begins to drop. How? Each rotary valve is not a dumb tube. It is connected to a real-time pressure sensor. This sensor constantly monitors the pounds per square inch inside the tire. The signal from this sensor travels through a small cable, protected next to the axle, to the CTIS Electronic Control Unit, ECU, the brain we are talking about. This journey of data from the rotating wheel to the stationary computer is another small miracle of connectivity that occurs in milliseconds. The brain processes the information. Tire 3, right rear axle, pressure dropping 2 psi per second, critical leak identified. Immediately, it activates a two-phase protocol. First, the human alert. In the cab, a warning light comes on in the instrument panel, or a digital display shows an unmistakable message. Pressure loss, wheel 3R. The driver is informed, not alarmed. He knows exactly what is happening and where. Second, and simultaneously, the automatic response is activated. The brain commands a solenoid valve to open the airflow from the truck's main reservoir to that specific wheel. The system attempts to counteract this by inflating the tire at the same rate it is losing air, keeping the pressure stable. This flow of information and action, from the periphery to the center and from the center to the periphery, turns a potentially fatal emergency into a managed incident. The driver is not blind. The truck is not helpless. The system has raised a shield of data and compressed air between failure and disaster. The ironclad decision, why the system would rather leave you without a wheel than without brakes. But what if the damage is fatal? What if the cut is so large that the air escapes faster than the compressor can replenish it? This is where CTIS reveals its true intelligence and makes the coldest, most logical decision a machine can make. To understand it, we must remember where the air it uses comes from. In a heavy truck or bus, compressed air is a vital and shared resource. The same compressor that feeds the CTIS is what powers the air brakes, the air suspension system, and other accessories. The air is stored in reservoirs or air tanks as a strategic reserve. The CTIS has access to this reserve, but it does not own it. It is a tenant with a very strict contract. The CTIS's brain is programmed with an unbreakable law, a hierarchy of survival. The integrity of the braking system is absolute and non-negotiable. Therefore, the system has sensors that monitor the pressure in the main air tanks. If it detects that the tire leak is so severe that it is dangerously depleting the air reserves, jeopardizing the pressure needed to apply the brakes with full force, it activates the sacrifice protocol. Mercilessly, without hesitation. It closes the solenoid valve that feeds that wheel. It cuts off the supply. It abandons the tire to its fate. In the cab, the alarm changes from inflating to critical leak, system closed. It would rather have a tire completely disintegrate, leaving the wheel a smoking rubber stump, than allow the truck to lose its ability to brake. It is an ironclad decision. A blown tire is a controllable accident, a costly mechanical disaster. A 40-ton truck without brakes is an uncontrollable ballistic missile, a tragedy of incalculable magnitude. The CTIS, in its cold algorithmic logic, chooses the lesser evil. It chooses to save lives, even if it means destroying a part of its own body. This ability to make life and death decisions sets it apart forever from being a simple inflator. It is a guardian with judgment. More than air, the system as the first responder to an emergency. Until now, we have viewed CTIS as a defensive system. It detects, alerts, compensates, and ultimately sacrifices to protect the greater good. But its role does not end there. In certain high-demand scenarios, it becomes an active first responder, capable of altering the very characteristics of the vehicle to overcome a crisis. This capability is rooted in its military origins, which we will discuss in later chapters, but its commercial application is just as vital. Imagine a service truck in an open pit mine, or a rescue vehicle stuck in sand, mud, or deep snow. A fully inflated tire, with its small, hard footprint, will sink. The solution is to deliberately deflate the tires to widen their footprint, distribute the weight, and gain traction. Doing this manually, in the rain, on dangerous terrain, with 18 wheels, is a task that takes hours and is extremely risky. With CTIS, the driver does not need to leave the cab. From a control panel, they can select an all-terrain mode or mud mode. The system obeys, opening the bleed valves on the drive wheels or all wheels, releasing air in a controlled manner until a predetermined pressure is reached, perhaps half the normal pressure. The tyre footprint flattens, transforming from a narrow circle into a wide platform. The truck gains the traction it needs to get out of the quagmire. Once on solid ground, the driver selects road mode. The system restarts the compressor and brings each tyre back to its optimal travel pressure, all automatically and synchronously. In this role, CTIS ceases to be a passive guardian. It is a dynamic transformer. It is the tool that allows the same vehicle to be both a highway runner and an explorer of extreme terrain, adapting its physiology to the demands of the moment. It not only responds to danger, it prevents it, giving the driver a superpower, that of altering the physics of traction at the touch of a button. Thus, that small rotating tube reveals itself not only as a sensor and an inflator, but as the gatekeeper of a realm of tactical possibilities that remain hidden from plain sight, ready to be summoned when the road disappears and only the pure challenge of reaching the other side remains. We have already revealed CTIS as a safety hero, a guardian that works in the shadows to prevent disasters. But in the world of commercial transportation, heroism must be translated into numbers. Survival is the minimum requirement. Profitability is the daily goal. Now we will delve into the territory where engineering decisions become columns of profits and losses. Here, compressed air ceases to be a vital fluid and becomes currency. Every pound per square inch of pressure represents a compromise between today's cost and tomorrow's savings. Far from being a frivolous expense, CTIS is the most meticulous accountant on board, monitoring one of the most stealthy and destructive capital leaks that exist: incorrect tyre pressure. The invisible anchor, how an underinflated tyre burns money litre by litre. To understand the economics of CTIS, we must first visualize a silent enemy: rolling resistance. A perfectly inflated tyre is an almost rigid circle that rolls with minimal deformation. It is efficient. But when the pressure drops, even slightly, the rubber softens. The contact patch with the asphalt flattens and widens. Now, with each revolution, the tyre doesn't just roll, it squashes. This cyclical deformation, this constant kneading of the rubber against the ground, is work. And that work requires energy. Energy that comes exclusively from the engine and therefore from fuel. A deflated tyre is an invisible anchor that the truck must drag along with it every metre of its journey. The numbers are eloquent and ruthless. Industry and tyre manufacturer studies estimate that a pressure 20% below the recommended level can increase rolling resistance by 10%. That 10% resistance translates directly into an increase in fuel consumption of between 4 and 5%. It seems like a small amount, right? It's a dangerous deception. Let's break it down. Imagine an 18-wheeler with a trailer. A single tyre, out of 18, with 20% low pressure, robs the entire rig of 4% efficiency. If not one, but several tyres are slightly underinflated, a situation more common than you might think, the waste is multiplied. On a 1,500-kilometre trip, that little bit can mean dozens of litres of diesel burned without producing a single useful kilometre of transport. The fuel is converted into heat, friction, rubber fatigue, and smoke that leads nowhere. CTIS eradicates this waste at its root. By keeping each tyre at its optimal cold inflation pressure, with minimal deviation, it eliminates invisible anchors. It ensures that every litre of fuel purchased is used entirely to move the load, not to fight against the vehicle's own deformation. In a business where margins are measured in cents per ton-kilometre, this tyre watchdog pays for itself over and over again at every gas station bill. Extended life. Why perfect pressure is the best antioxidant for rubber. If fuel economy is the immediate argument, tyre longevity is the equity argument, protecting the most expensive capital investment after the truck itself. A steer or drive tyre on a heavy truck can cost hundreds, even thousands of dollars. And a complete set for an entire road train represents an astronomical sum. This investment is not an expense, it is an asset that must be amortized over the longest possible distance. And nothing kills a tire faster than the heat generated by excessive flexing. When a tire rotates at low pressure, its sidewalls bend violently with each rotation. This constant flexing generates internal friction between the layers of rubber, canvas, and steel that make up the tire. Friction turns into heat, and heat is rubber's mortal enemy. It degrades the chemical compounds that give it elasticity and strength, accelerates cracking, and can even cause the inner layers to peel away in a catastrophic phenomenon called tread separation. Even without reaching catastrophe, heat and uneven deformation wear the tread unevenly, creating sawtooth patterns or shoulder wear, which drastically reduces its useful life and its ability to be retreaded, a process that can extend the life of the tire by 60 or 70%. CTIS, by ensuring constant and correct pressure, eliminates excessive flexing. The tire works as designed, rolling, not twisting. Internal temperature remains within safe ranges. Treadwear is uniform and predictable. Studies of fleets equipped with CTIS report increases in tire life ranging from 20 to 30%. This means that instead of replacing a set of tires every 200,000 kilometers, a fleet can do so every 250,000 kilometers or more. Multiply that 20% extra life by the cost of 18 high-end tires, and the savings is a number with many zeros. CTIS is not an expense. It is an accelerated depreciation fund for tires. It is the best insurance policy against premature degradation, a policy that pays dividends in the form of rubber that lasts miles and miles longer. The cost of ignorance, simulating a fleet without CTIS versus one equipped with it. Let's take this arithmetic to a concrete level, to a simulation that any fleet manager performs with pen and paper or with a sophisticated spreadsheet. Let's compare two hypothetical fleets, each with 100 identical tractor trucks, each traveling 120,000 kilometers per year. Fleet A operates using the traditional method, manual tire pressure checks every few days, relying on driver discipline and maintenance rounds. Fleet B is equipped with factory-installed CTIS. Let's start with fuel. Let's assume a base consumption of 3 kilometers per liter. In Fleet A, with at least a couple of tires constantly slightly underinflated, a statistical reality, consumption is reduced by 3%. That's thousands of extra liters per truck per year. Multiplied by 100 trucks and the price of diesel, the annual difference in the fuel bill is a sum that easily exceeds $500,000. Fleet B saves that amount. Let's continue with the tires. Fleet A, with its uneven wear and greater thermal stress, replaces complete sets 20% more frequently. If a complete set costs $15,000, the additional annual replacement cost is staggering. Fleet B stretches that investment, saving another $250,000 or more on tires per year. Now let's add in downtime. A critical flat tire in Fleet A requires an emergency stop, a call to a roadside tow service, paid driver hours without production, and the loss of the scheduled load. Each such event costs thousands of dollars in lost productivity and extra expenses. Fleet B, with its early detection and automatic compensation, can, in most cases, make it to a scheduled repair shop without emergency stops, turning a drama into a simple maintenance appointment. When we add up all these variables, fuel, tires, downtime, labor costs for manual checks, the difference in total cost of operation, TCO, per kilometer between the two fleets is staggering. The cost of installing CTIS in Fleet B typically pays for itself in less than 2 years. From then on, it's pure profit. Fleet A operates in ignorance, paying a hidden tax on inefficiency. Fleet B operates intelligently, turning every pound of pressure into a penny of profit. The ecological dividend: less smoke for more miles. In an era of climate awareness and increasingly stringent environmental regulations, efficiency is no longer just a matter of internal accounting. It is also a social license to operate. Here, CTIS generates what could be called an automatic ecological dividend. Let's remember the fundamental equation: lower rolling resistance equals lower fuel consumption. Lower fuel consumption equals less carbon dioxide emitted into the atmosphere per ton transported. It's pure mathematics. A truck with CTIS, by burning fewer liters of diesel to do the same job, directly reduces its carbon footprint. But the environmental benefits don't end there. Longer-lasting tires mean less rubber waste to manage. Fewer tires are discarded prematurely in landfills or sent for energy-intensive recycling processes. In addition, a tire that wears evenly and maintains its structural integrity is a perfect candidate for retreading, a practice that is the essence of the circular economy in the transportation sector. Retreading can extend the life of a tire casing, the most valuable and complex part to manufacture, over 3 or 4 useful lives, saving a monumental amount of raw materials, energy, and emissions associated with manufacturing a new one. By maximizing the life of the casing, CTIS becomes a key ally in this circularity. For large logistics companies, this ecological dividend is not just a good headline in a sustainability report. It is a tangible business argument in the face of increasingly demanding customers with green supply chains and a shield against future carbon taxes or tougher efficiency regulations. The right air in the tires thus becomes an instrument of environmental policy. Why your car will never have this and why that makes sense. After exploring all these advantages, safety, savings, durability, ecology, an inevitable, almost common sense question arises. If CTIS is so wonderful, why doesn't my car, or any pickup truck, have it? The answer reveals a fascinating paradox about economies of scale and the risk-benefit ratio. The argument is not technically impossible. In fact, tire pressure monitoring systems, TPMS, exist in most modern cars. But a TPMS is only half of a CTIS. It is the sensor, the alarm. It lacks the active part, centralized automatic inflation. For a car to have a complete CTIS, it would need a dedicated air compressor, a storage tank, a network of high-pressure pipes to all 4 wheels, and 4 precision rotary valves. The cost, weight, and complexity of adding this entire system to a 1 or 2 ton vehicle is disproportionate to the benefit. The risk it mitigates, a flat tire, is manageable for a private driver, and the fuel savings on a scale of 4 small tires and already low consumption would be minimal, taking years to recoup the investment. In a truck, the equation is radically reversed. The cost of the CTIS system is a tiny fraction of the total price of a vehicle that costs hundreds of thousands of dollars. The risk it mitigates, a catastrophic blowout with 40 tons, is on a societal scale. And the savings it generates, multiplied by 18 giant tires and monstrous fuel consumption, are massive and rapid. It is the law of return to scale. What is an unjustifiable luxury for one is an absolute economic necessity for the other. The truck can justify complex engineering because its numbers are big. Big weights, big distances, big costs, big risks. CTIS is proof that sometimes the most sophisticated and expensive solution is, in the right context, the simplest and most economical. It is the paradox of the truck. It needs more complex technology than a car precisely because its world is simpler in its brutality. A world where every variable, every PSY, every litre, every kilometre of rubber is subject to such ruthless and clear arithmetic that only an automatic and tireless guardian can guarantee that the final sum will be positive. The history of CTIS did not begin in a truck factory or on a civil engineer's drawing board. It began in the blood-stained mud of an invasion beach under artillery fire, where the need was not to save money, but to save lives. It is time to trace the epic journey of a technology forged in the chaos of war, refined in the harsh trials of commerce, and elevated to its highest expression in the most extreme environments on the planet. To understand this journey is to understand why a seemingly mundane system like tire pressure monitoring carries with it the weight of history and the promise of the future. Birth in hell, the amphibious duck and the wartime need to stay on board to inflate. These were the years of the most devastating global conflict in history. On the European and Pacific fronts, mobility was synonymous with survival. And one of the strangest and most vital vehicles of that conflict was the DUKW, affectionately nicknamed the Duck. It was an amphibious truck, capable of rolling on land and sailing on water, designed to carry supplies from landing craft directly to the beach and beyond. But these beaches were not made of fine sand. They were traps of deep mud, loose gravel, and deadly obstacles. A fully inflated tire designed for the road would sink hopelessly into such terrain. The manual solution, getting out to deflate the tires with a wrench under enemy fire, was a death sentence. Brutal and urgent necessity gave birth to innovation. US military engineers, in collaboration with the Goodyear Company, developed the first centralized tire pressure control system. From the relative safety of the cab, the duck's driver could flip a switch. This activated a system that, through pipes and valves, released air from the vehicle's 6 large tires, flattening them to transform their footprint. Suddenly, the duck no longer sank. It floated on the mud. It gained traction to get off the beach. Once on solid ground, the driver reversed the process, and the system, connected to the engine's compressor, re-inflated the tires to regain speed on secondary roads. This was not a technology of convenience or economy. It was a tactical force multiplier. It meant that a single vehicle could adapt to multiple terrains without stopping, without exposing its crew. It meant that supplies reached the front lines. In the hell of war, central control of tire pressure was not a feature, it was a vital organ. From the beaches of Normandy to the jungles of the Pacific, this system proved that the true power of a vehicle lay not only in its engine, but in its ability to reconfigure its contact with the ground. And that lesson, learned at such a high cost, would not be forgotten in times of peace. From soldiers to truckers, the migration of military technology to commerce. When the guns fell silent, a vast amount of technology and knowledge became available. Engineers, designers, and visionaries began to look at the civilian world with new eyes, wondering which tools of war could serve reconstruction and growth. The duck system did not go unnoticed. In the 1950s and 1960s, as the interstate highway system in the United States expanded and truck transportation exploded, the problems were different, but the logic was similar. Trucks began to travel continental distances, carry heavier loads, and face extreme weather and difficult terrain on infrastructure projects. The idea that a driver could adjust the pressure of their tires for a heavy load on the highway and then slightly deflate them to maneuver in the mud of a construction site was tremendously appealing. Thus began the slow but steady migration. First, in specialized vehicles, forest fire trucks that needed to venture onto dirt roads, oil exploration vehicles, service trucks on large construction sites. The first civilian versions were crude, almost direct replicas of the military system, but they proved their worth. The qualitative leap came with electronics and advanced materials. Rotary valves became more reliable, electronic pressure sensors replaced mechanical ones, and control units went from pneumatic levers to small computers. What began as a tactical survival tool was refined into a tool for economic optimization. The truck driver was no longer a soldier avoiding enemy fire, but faced other enemies: delivery deadlines, fuel costs, maintenance budgets. CTIS was put to work in this new battle. The migration was complete. The technology had crossed the line, proving that an innovation forged to save lives in chaos could, with the right approach, save businesses in a competitive market. The giants that need it: CTIS in open-pit mining and the value of a tire. If there is one place where the risk-benefit equation of CTIS reaches its purest and most dramatic expression, it is in open-pit mines. This is where the world's largest vehicles operate, mining haul trucks, monsters 2 or 3 stories high with wheels twice the height of a person. In this environment, a tire is not a component, it is a monumental capital investment. A single tire for one of these giants can cost between $50,000 and $100,000, and a truck can carry 6 of them. The cost of a complete set is close to that of a mansion. But the cost of failure is infinitely greater. A blowout in one of these tires, due to a cut from sharp rock or overheating from low pressure, is not an inconvenience. It is a high-risk production shutdown event. The sound is like an explosion, capable of severely damaging the truck, and the shattered wheel can become a deadly projectile. Stopping one of these behemoths to change a wheel in the middle of the mine pit is a logistical operation that can take an entire day, involving special cranes and high-risk equipment, halting the entire production chain. Here, CTIS is not an option. It is the vehicle's circulatory system. It monitors each tire with obsessive precision. In these trucks, the system not only compensates for minor leaks, it is programmed to dynamically adjust pressure according to the load. An empty truck on its way to the pit can carry 1 pressure. A truck loaded with 300 tons of ore carries a higher pressure to withstand massive deformation. Furthermore, on the long, steep exit ramps from the mines, heat is the great enemy. CTIS helps manage it by ensuring that pressure never falls below the level that would cause catastrophic flexing. For mine managers, CTIS is a first-rate asset management system. Every pound of pressure monitored is $1 protected. Every early warning prevents a 6-figure loss. In this realm of giants, the small rotating tube becomes the guardian of a treasure, proving that its value is directly proportional to the value of what it protects. The farmer's touch, variable pressure to avoid crushing the future harvest. At the opposite end of the scale, but equally vital, is the field. Modern agriculture is not done with small tractors. It is done with steel behemoths of hundreds of horsepower, with tires as tall as a person, pulling seeders, cultivators and harvesters of enormous widths. The enemy here is not rock but soil compaction. When a heavy tractor drives through a field on high-pressure tires, its wheels act like invisible plows, crushing the porous structure of the soil. This destroys air and water channels, hinders root growth, and over time dramatically reduces crop yields. The agricultural solution from CTIS, often called a variable pressure system or VT1, is a work of agronomic precision. When out on the road moving between fields, the tractor inflates its huge tires to high pressure for efficient rolling. But when it reaches the edge of the field, the driver activates field mode with the push of a button. The system releases air in a controlled manner, dramatically widening the tire's footprint. The tractor's weight is then distributed over an area 2 to 3 times larger. The pressure on the soil drops to levels that do not damage it. The tractor literally becomes a lighter vehicle for the land. This allows it to work in optimal moisture conditions without sinking, preserving the precious soil structure. When finished, the system re-inflates the tires for the return trip. The impact is profound. Less compaction means better water infiltration, less erosion, healthier roots, and ultimately more abundant and sustainable crops. In this context, the CTIS is no longer merely a tire protector. It becomes a soil protector, an instrument for conserving and maximizing the most valuable resource, fertile soil. It is the perfect fusion of heavy engineering and biological sensitivity, a technological bridge between steel and life. The future of the Guardian: sensors, telemetry, and the wheel that talks to the cloud. Today, the evolution of CTIS continues unabated. It is being absorbed by the biggest wave of the era: digitization and interconnection. The future is not just a system that monitors and acts on board. It is a system that observes, analyzes, predicts, and communicates. New generation sensors in each rotary valve no longer measure only pressure. They measure the internal temperature of the tire in real time, critical data for predicting failures. This data travels via wireless connections within the vehicle, not cables. The onboard control unit is no longer an isolated brain, it is a node in a network. Using telemetry and connectivity systems such as GSM, all information from the 18 tires, pressure, temperature, alerts, is transmitted in real time to a cloud platform. In the fleet manager's office, a map shows the location of each truck, and a control panel indicates the health of each wheel with color codes. The system no longer alerts only the driver, it alerts the dispatcher and the maintenance manager. It can generate automatic work orders when it detects a pattern of slow pressure loss, scheduling a repair at the nearest repair shop along the route before a breakdown occurs on the road. Using artificial intelligence, these systems begin to learn. They can correlate an abnormal temperature increase in a specific tire with a pattern of rough driving or a route with many sharp turns, suggesting adjustments. They can predict, based on historical data, the remaining life of each tire with astonishing accuracy, optimizing the timing of retreading or replacement. The future of the Guardian is to be omnipresent and omniscient. The wheel is no longer a silent component. It becomes a constant source of data, an oracle that speaks of the condition of the vehicle, the quality of driving, and the risks of the road. The small rotating tube will be just the physical port of a universe of information, the point where the analog world of rubber and asphalt meets the digital world of bits and clouds to create safer, more efficient, and more predictable transportation than ever before. So, the next time that little spinning metal tube catches your eye, remember that it is not just another part. It is the physical witness to an epic journey from the battlefield to the data center. It is the materialization of a simple idea, the right pressure, elevated out of necessity to the status of an intelligent and vital system. It reminds us that behind every detail on the road, no matter how small, there may lie a story of human ingenuity, a battle against risk, and a promise of efficiency. It is a silent reminder that progress often revolves around the most fundamental ideas, guarding them with the most exquisite complexity.